19th lecture on this machine course, and in our last class we did one very important thing. That important thing is that basic building block of any rotating machine, apart from stator iron, rotor iron, slots, and slots will house windings. So, ultimately the basic building block is a coil side. Okay. Then from that we went further ahead and told that basic building blocks will be a single coil. A coil, single coil, if you recall, it has got two coil sides, and they will be placed in slots. It is better to repeat that. This is how, and it could be a multi-turned coil. So, henceforth this will be my basic building block of any rotating machines. There may be number of coils present, but each coils will be identical, but only thing they will be placed in some other slot. This coil and this coil, these two coils are suppose identical, and they will be placed in some other slots. And when these things will rotate, move relative to a sinusoidally distributed magnetic field, there will be induced voltage across the two terminals of the coils. And the terminals, you should note that this point is 1 and this point is 1 dashed. This is second coil, it should be also named 2 dashed, and things like that. So, in our last class what we did that we found out the expression of the induced voltage in a single coil as E11 dashed RMS value. This RMS I will not write henceforth, but for the first time let me write root 2 pi P n by 2 root 2 pi, then I wrote phi, and then I wrote capital N. What are these things? These things are phi is flux per pole, flux per pole in Weber, Weber per pole, and its expression for a multipolar machine we derived as 4 by P B max L into R. L is the length of the machine, that is active length of the conductor, active length, and R is the radius of the rotor, radius of rotor. So, this is in terms of flux per pole. And what is this N? N is the mechanical speed of rotor in RPS, and this F is nothing but the P n by 2, P n by 2. So, for a generator input should be the speed. So, speed appears here, but we will write it like this root 2 pi f phi into n. So, that is the RMS voltage induced in a particular coil. This equation similar to that of a transformer, but in case of transformer remember the RMS voltage in transformer is root 2 pi f phi max into n. So, it is phi max there, but it is phi, okay, for different reasons. So, it is easy to remember a formula. Now, and the idea was that this was I assumed the flux density was sinusoidally distributed. In space, this is space angle without anything written, it means it is electrical, and this is B max. And if you imagine your coils are staying here at t equal to 0, 1 dashed, coil span should be 180 degree electrical. So, this is always 180 degree electrical, these angles. So, this is how B is distributed, and if this coil moves, there will be AC induced voltage in that. The RMS value of that AC voltage is this one. Now, this tangential velocity V was converted to the angular speed like this by noting that position theta is nothing but omega t. At any time t, the coil, new position of the coil will be say here, as it is moving with a speed omega radian per second. So, this was at any instant t, this was omega t, and one will come here, 1 dash will go there, and relative to this it is moving. So, all these things we did last time. Now, only one thing I would like to tell. I was telling you many a times that after all, if you have a single coil, just listen. If you have a single coil, the flux density distribution will be rectangular in shape, is not? That is what I was telling. South, north, they will go like this, and this is your space angle theta. Now, if you have a rectangular distribution, then what will be the induced voltage? Okay, induced voltage will be similar to this, because it follows the same path, same pattern as that of B. If this is B, this will be your induced voltage E 1 dashed, instead of sinusoidal if you are having. But the another way of looking at it, so you find out this sinusoidal voltage, and then you suppose want to examine, okay, how much of it is fundamental component and what are the harmonic components of the voltage. One way of doing is, this is rectangular, you find out voltage pattern which is also periodic, simply Fourier analyze this. Of course, in this case the RMS voltage should not be calculated by this formula, obviously, because it is not sine wave. But I know given a periodic waveform how to calculate the RMS voltage, etc. But anyway, this periodic wave can be broken up into fundamental component and third harmonic, fifth harmonic, all odd harmonics will come. That is, this voltage waveform can be found out fundamental, then third harmonic, then fifth harmonic, and for each one of them this RMS voltage formula will be valid, because each one of them is sinusoidally distributed. Another way of doing it, then it will be clear what exactly I am trying to tell, that you can suppose your B distribution is rectangular, single coil, multi turn, etc. So, this is suppose only one cycle I am drawing. This is the plus B and this is minus B, and this is all electrical theta, and this is 0, this is pi, this is 2 pi. Now, if you break it up into a fundamental component, this is theta and this is your pi. So, your fundamental will be this one, and this is the B max sin theta fundamental component. Say, let me write B max 1 sin theta. This is the fundamental component. Now, there will be next higher harmonics which will be present will be third harmonic. Only for that third harmonic I will show you how to calculate the voltage, and then we will be able to do it for other higher order harmonics, for example, fifth, seventh. But I am sure about one thing, that this amplitude of these harmonic components will progressively decrease. No point in taking 13th harmonic component to calculate the voltage, because they will become negligibly small. Because those who have done Fourier analysis know that higher order components amplitude will go on decreasing. But once you break it up into sinusoidal distribution, each of the component, then you will be able to apply these formulas. Why not? Because this is valid for sinusoidal thing. So, this is the thing. Now, the third harmonic component. What is the third harmonic component? Third harmonic component of B max 3 will be also sinusoidally distributed, but when the fundamental makes one complete cycle, your third harmonic will make 3 complete cycles. That is why it is called third harmonic. So, let me divide these things with 60-degree intervals. Okay. Each one is 60 degree, this red marking, this is 60, 60. So, this the B max 3 will have 3 cycles. One cycle will be like this. Next cycle will be like this. Oh, sorry. One cycle 120 degree, next cycle next 120 degree, and the third cycle is here. So, 3 cycles of this can be, its equation is B max 3 sin 3 theta. Similarly, if you wish, you can sketch fifth harmonic. In one cycle of fundamental, there will be 5 such cycles, but I am not going to draw those things. If I understand how to tackle one harmonic component, you can easily figure out what to do. So, this is the thing. Now, this B max 1, B max 3, their magnitudes I will get after Fourier analyzing this. If I know this B value, I will be able to find out some expression, and these amplitudes are known. Now, if I write it, the voltage 1 dashed fundamental component, it will be root 2 pi p n by 2 that is f, fundamental frequency f, 2 pi f, flux per pole of fundamental into number of turns, that will be the RMS voltage. Now, the question is what will be voltage across 1 dashed due to the third harmonic, I want to find out. So, to find out that, I must know what is the flux per pole due to the third harmonic component. Now, if you look at it, if you concentrate your attention on the third harmonic component alone, fundamental we have done. So, idea is find out third harmonic component, fifth harmonic component, add them up to get the total voltage. Now, if you look at it, third harmonic component, how many poles this machine has got? If P is the number of fundamental poles, fundamental component poles, number of poles created by say kth harmonic will be simply Kp. Suppose your original number of poles P equal to 2, if it is third harmonic, 6 poles are created. Okay. Therefore, third harmonic component, so this is south, this is north of the fundamental. You see there is south, north, south, north, south, north. So, 6 poles will be created because of third harmonic. So, 3 P for example, it will be like this. Therefore, that is the thing, and n is the mechanical speed. Therefore, wherever P is there, it should be Kp now. So, it will be, so to calculate flux per pole for Kp any order harmonic, it will be 4 by P B max of that component into Lr, but P in this case is Kp. Number of poles has increased. Therefore, 4 by Kp into B max K into Lr. Therefore, E11 dash third harmonic component will be root 2 pi, wherever P is there it should be Kp, in fact it is kth harmonic in general, kth harmonic, root 2 pi Kp n, because number of poles for this particular kth harmonic has increased by Kp. So, Kp n by 2 into phi flux per pole due to that kth component, which should be calculated by using this. B max L R are fixed, I mean B max K you have to take, and 4 by Kp, because number of poles of that machine has increased. So, root 2 pi this thing into phi Kp into n, number of turns of course remains same. Now, as I told you, so this is how RMS value of 1 dashed across the same coil, because of third harmonic component, fifth harmonic component can be calculated by putting appropriate value of K, but don't forget to calculate phi 3 P, phi 5 P in this formula, depending upon which harmonic voltage you are calculating. Fifth harmonic component, its amplitude will be further less. So, this should be remembered. And another thing, you see, the span of the coil is 180-degree electrical is always with respect to the fundamental component. As I told you, if you place the 1 here, this 1 dash should be placed such that it is 180 degree, is not electrical. So, 1 dashed will be placed here at the center of the south pole, 1 dashed. Now, what about this third harmonic component has been created, it will be there, I cannot help. If this is the wave, then due to the third harmonic component, once again is it true that when 1 is under one of the pole center, 1 dash will be under the opposite pole center? Yes, it is true, because it is now you see under this pole center and this is opposite pole center. Therefore, once again EMF will be added up. So, odd harmonics, fifth also. So, 1, 2, 3, 4, then that thing comes. Therefore, you can easily verify that all harmonics, odd harmonics will induce a little bit of voltages depending upon their strength B max k, and they will be added up. Of course, there may be plus and minus sign before the Fourier coefficients, that can be easily taken care of. So, to use this formula to calculate the flux per pole for kth harmonic, you have to do like this, use the same formula 4 by p B max L, but if it is kth harmonic of B distribution, then the number of poles are really k into p times. If it is originally 4 pole machine, because of fundamental, it will become 12 poles, is not. So, that is very interesting. But in any case, as I told you, if you are using multiple coils, your B distribution may be like this. If your B distribution is like this, then once again do the Fourier analysis of this waveform, get the fundamental. These amplitudes will be known if you are using distributed coil, not a single coil. There are 2 coils connected in series in order to achieve more sinusoidal distribution, more nearer to a sinusoidal flux density distribution. Then also I can find out this is a slightly involved waveform, but nonetheless it can be easily done. I can find out phi k p, put k equal to 1, get the fundamental flux per pole and so on, and get the RMS value of each one of them. And what will be the RMS value of this waveform? This can be also calculated by squaring each of the RMS voltages and summing them up and finally taking one square. For example, E RMS of this voltage waveform, in general if harmonics are present, you are not neglecting, it should be done like this: E 1 dashed only fundamental square plus E 1 dashed only third harmonic plus E 1 dashed only square kth harmonic. I mean dot dot dot, add all this 1, take under root, get the RMS, and you will get the same expression. If you know B waveform, this RMS you calculate, this square wave, you will get that. So, just to point out that the odd harmonics, if it is present, all the odd harmonics will once again you can see the one conductor is placed under the center of a particular pole, other coil side, which I have already placed based on my requirement fundamental thing, that will be also under the opposite pole, and you can calculate the voltages. So, this is the thing you should remember to conclude this part. Therefore, this expression is the most important one. N is the mechanical RPS, okay, mechanical RPS speed, phi is the flux per pole, and we will generally neglect the harmonics because of the fact we will see. I will try my best to make the B distributions as close as sinusoidal, so that harmonics can be neglected. So, in this lecture what I have done, I have told another important thing to conclude this, that okay, if even if B distribution is not is square step type like this or this, and if you are using a single coil it will be like this only we have seen, then we know it can be broken up into fundamental, third, fifth and so on. So, I will do Fourier analysis, and this is suppose the fundamental component, and based on this fundamental component coil span has already been fixed, and this I cannot change. I have fixed up the coil sides into identified two slots where this angle is 180 degree electrical. This I cannot do anything, that is fixed. So, now what is happening? Fundamental component is there, then third harmonic little amplitude third harmonic component will be there, and this fellow is rotating. So, so far as third harmonic is concerned, it looks like it has become a 3p pole machine, and if it is 3p pole machine, will there be also voltage across 1 dash? Yes, there will be, simply because if one conductor wherever you have placed under center of one says north pole, the other one I find it is under the center of south pole, and therefore, there will be voltage. This is also true for fifth and seventh harmonic. And can I use the formula we have already derived? Yes, you can use, provided you are careful. Suppose I want to find out the RMS voltage contributed by the kth harmonic component of B distribution, then E 1 dash kth should be root 2 pi, and this is about the frequency term or the speed term n, and it has number of poles of this machine is now K p, so far as kth harmonic is concerned. So, P should be replaced by K p wherever it is there n by 2, and this one therefore, looks like root 2 pi K into F, where F is the frequency of the induced voltage due to fundamental, and this is phi K p. What is phi K p? Phi K p is, we know, 4 by P B max into L r. For a original machine P pole, for kth harmonic number of poles has increased, it has become K p poles, because over same degree of mechanical separation so many poles are present. So, 4 by K p B max K, kth harmonics amplitude B max K is this one into L into R. L R of course, will not change, length of the machine is fixed, R is fixed. We will continue next time. Thank you.